So today we'll be talking about the kinetic model of matter. Okay, first thing first, I need you all to take out a paper and pen and jot down any key ideas that is unfamiliar to you. Okay, I'll be going through quite fast the first part, okay, until we reach a new familiar phase, because I'm quite sure this has been touched on during chemistry, that this is a solid, that this is a liquid, and the last diagram here is a gas. Okay, now I'm sorry if you all hear background noises. Okay, remember to comment and give constructive feedback on how we can improve this and how we can improve your learning process. Okay, if this is better or is classroom experience even better. Okay, so yeah, we'll just do what is better for you guys. Okay, so now for this chapter, right, there's quite a few objectives. But today we'll be looking, I think, at the first four. Okay, we might be looking at this. Okay, if there's time. The video is aimed to be finished in less than 10 minutes, so I do not want to drag. If it is not possible to finish, I'll not do it. Okay, so we'll be looking at states of matter and Brownian motion. Okay, for states of matter, it'll be quite simple. For Brownian motion, I think it's something new. Okay, however, if we are not able to finish the states of matter, I'll not go into Brownian motion as well. Okay, so we'll start. Now, the first two things that we want to discover is comparing the properties of solid, liquid, and gases. Okay, followed by describing the molecular structure of solid, liquid, and gases. Okay, so if you were to look at the next few diagrams, okay, that I made here, okay, it should appear to you, it should appear to you that this is solid, this is liquid, and this is gas. Okay, intuitively this should come to you. Okay, this has been taught in Sec 2. If you have issues with this, you can come look for me again. Okay, I'm not going to go through this. Okay, now there's this idea that physicist came up with about 5 centuries ago. Okay, the idea between Isaac Newton and someone else. Okay, so it says that the closer particles are together, okay, the closer they are, it will mean that there's a greater intermolecular forces. Or rather, if we are just talking about two particles, then it will be greater intermolecular force. Okay, I'm going to use a short form here. Intermolecular force will be called IMF. Okay, so for solid, because the particles are close together, okay, for solid, the particles are close together, so we expect a great intermolecular force. Okay, yeah, for liquid, however, they are not so close together. Okay, in fact, the arrangement is irregular, however, to a confined space. Okay, so we call this a moderate amount of intermolecular force. Okay, and the last one, for gas, we all know that for gas it is for gas, the arrangement is irregular and it is random. Okay, so we expect a weak intermolecular force. Okay, so these are the relation with regards to intermolecular forces. So I need you all to know this. Okay, actually, you just need to understand this principle and you'll be able to, you don't have to memorize, right? You don't have to memorize that solid has great intermolecular force. You just need to know this principle and it will be applicable to solid, liquid, and gas. Okay, now as you can see from the diagram, or as you have already know, for solid it can vibrate at its position. Okay, I'll show you an animation on that. Okay, yeah, over here you do realize that the solid here is vibrating at its own position. For liquid, okay, the particles are moving in random. Okay, however, they are moving within a confined space. If you all can see, I'm drawing a rectangle here. Okay, there's a confined space here, so they only move within that confined space. However, for gas, right, the rectangle doesn't apply to them anymore. Okay, so for gas, the movement is random and it's really moving in a random space. Okay, there's no confined area or space for to define, oh, the gas is only moving within this area or the gas is only moving this area. Okay, the entire area belongs to gas. Whereas for liquid, okay, if you take a look again, it's really only within this rectangle that I'm drawing right now. Okay, so that's it for the three kinetic model for solid, liquid, and gas. Okay, now I'm more interested in knowing the graph that that relates to the kinetic model. Okay, so strictly speaking, okay, yeah, when you are experiencing a absorption of thermal energy, okay, so when you absorb thermal energy, okay, uh, we will expect a rise in temperature. Okay, this is also intuitive. Okay, I believe most of us agree that when you absorb thermal energy, your temperature should increase. However, it is not true for all cases. Okay, so in fact, you can actually see from this graph that this is a temperature graph against the heat energy supplied. Okay, so what it's saying is that as we supply more and more heat energy, the temperature of a certain particle or a model should increase. Okay, so you see that as the heat energy increases for this within this region, okay, let's call this ice, which is a solid, and let's call this water, which is a liquid, and let's call this steam, which is a gas. Okay, so we see that for an increment of thermal energy within this region for ice, okay, there's a increase in its temperature, which is true. Okay, we take ice out of the freezer, and then after a while the ice starts to become less and less cold. Okay, or rather in the right physics term more and more hot. Okay, but you don't really feel that the ice is hot, that's fine, and until when it suddenly starts to melt. Okay, now during the melting process you realize that, wait, there's no increase in temperature. Yeah, that's right. Because in the process of melting, the thermal energy is used to overcome intermolecular forces. Okay, so before it melts, okay, the thermal energy is used to make the particles vibrate. Okay, so when the particles vibrate, the vibration is also known as Ke. Okay, so uh, this Ke will be dissipated as heat. So your temperature increases. Okay, so Ke dissipated as heat, causing T to increase. However, when it's melting, okay, the thermal energy is used to overcome the intermolecular forces. Okay, so yeah, that is why in the process of melting the temperature does not increase. Now, if you are to do the same, okay, over here there's another process where state changes, okay, from water to steam, and that will be also known as boiling. Okay, if you are good, if you really understand what I mentioned 30 seconds ago, okay, this shouldn't come to you as difficult. You should be able to see that for boiling, okay, same thing, the thermal energy is used to overcome the intermolecular forces, so that the particles in the water, they'll be even more separated, such that they are so separated they behave like gas particles, and therefore water therefore becomes steam. Okay, same thing in the process of it before it goes to boiling, the process over here, okay, the there'll be vibration, which is your Ke, and same thing, the Ke will be dissipated as heat, and when Ke is dissipated as heat, we know that T will increase. Okay, so I hope you all understand the graph. Okay, the next thing is Brownian motion. Okay, it is the random movement of particles in a fluid. Okay, now I need you all to look at the link below, and you all may see the link and understand better what is Brownian motion. Okay, the link, when you look at the link, right, okay, it's over here. You all can start from 1 minute 17 seconds, and I need you all to notice, yeah, at one part of the video where the smoke particle seems to be moving on its own. So I want you to consider what is happening over there. All right, we'll talk more in class tomorrow. I'll end the online lecture here. Okay, hope this is going well. Okay, so I'll see you all tomorrow. Okay. Bye bye.